for three-dimensional problems, we need to use the inertia matrix. In that case, we're not going to use just one moment of inertia information, but we might as well use all the information inside this inertia matrix. In the tensor-wise notation, this is a second-order tensor, or else called as a dyadic, by the way. But if you're going to deal with this problem in terms of matrices, then this is a 3 by 3 matrix. The diagonals are the moment of inertia that are calculated about the axes chosen for that rigid body. And depending on the symmetry of that rigid body, you will have these off diagonals. They might come out to be all zeros. Then you have perfect symmetry. It's kind of like a cube or a sphere. Otherwise, you have these off diagonal elements, which are called the product of inertia. Now, if you're going to consider this for a three-dimensional object, let's try to draw a cube here. Those are two. I will be able to draw it, yes, and then we can talk about the axes here, x, y, and z axes. Maybe in the mass center. Usually we calculate it with respect to mass center, so we can call this x, y, and z. And the components on this diagonal of this 3 by 3 matrix are the mass moment of inertia calculated about this x, y, and z. And the reason that I have xx, because I could have also xy, ixy here, and that would be the product of inertia. So let's take a look at how we calculate these. The idea is the same, actually. So we're going to calculate, for example, izz. So this is our z-axis for this rigid body. This is a thin plate, but doesn't matter at the moment. If we're going to use this izz, then we need to find the distance information of this dm with respect to the x and y axes, and we're going to call the distance to the y-axis as x, and then the other one as y. Actually, what we are trying to calculate is r, and then in the formulation, what's going to appear is r squared, and r squared is calculated as x squared plus y squared. So that's why in this equation now we have x squared plus y squared times dm, and that would give us the information about mass moment of inertia about the z-axis with respect to our definition here. Iyy will be calculated in a similar way. In this case, instead of y, obviously we are trying to find out the distance to the x-axis along the z direction. So that's why we have x squared plus z squared. And ixx is the mass moment of inertia of this rigid body calculated about its x-axis. And these axes are something that we define, by the way. So in terms of a different type of a definition, that you're going to end up with a total different inertia matrix. For this cube, if you're going to assign, let's say, directions like this, then you're going to end up again with a different inertia matrix. But for a sphere, it's going to be the same. However, you define that, as long as you are within the mass center. However, you're going to define it, you're going to end up with the same mass moment of inertia. In that case, all the off-diagonal elements become zero, and then the diagonal elements become equal to each other because it's the same distance information. Anyways, going back to the product of inertia. Product of inertia is calculated in this way. So if you're going to consider, oops, and then there's a symmetry here, as you can see. So this is what we can deduce from this information. The inertia matrices are always symmetrical. So Ixy is equal to Iyx. If you need to calculate Iyz, then it's going to be x times z dm, and Iyz is equal to Izy because of the symmetry information. For the thin flat plates. By the way, if you're going to deal with the planar problems, all we need to know is mass moment of inertia. We're not going to consider the inertia matrices for planar problems. The only way that you're going to consider these is for three-dimensional problems, which is not the case for us, so you don't have to worry about this inertia matrix at the moment. But this is just extra information for you guys. Now, if you're going to consider thin flat plates, then we can use this idea about area moments of inertia. Now, the difference is that instead of mass, now we have area moments. And as you can see here, we don't only have this mass information here, otherwise it's kind of like the same idea. So if we're going to find out this area moment of inertia along the x-axis, we're going to use the y information here for the y-axis, x information for the z-axis, which is going out of the board here. Then this is this r distance, which is calculated making use of the x and y, so x squared plus y squared. So this r squared is actually equal to x squared plus y squared, and that is equal to ix plus iy. So this is about the area. This is just a two-dimensional object here. Now, if we want to integrate this information about the mass, then we do that by introducing this rho, which is the density of that material. Still, it's a thin plate. We're going to make use of the area moment of inertia. So this is y squared, and as a result of that, Ix times rho here again is the density, this is kilograms per meter squared, times t is the thickness. Now we get this mass moment of inertia information, which is derived for this thin plate. And similar to that, we get rho t times Iy, and then for the Iz set, again, we use this information of Ix plus Iy, or just r squared dA, and then rho times t times Iz gives us the information about the mass moment of inertia about the z-axis. Now, for the regular objects, already the information about the mass moment of inertia are already determined. So for a cylinder along this axis of symmetry, this is calculated as 1 over 2 mr squared. M is the mass of it, r is the radius. This is for the half cylinder. If we're going to think about the thin ring, this is the actually definition of this radius of gyration. So here mr squared, r becomes equal to the kappa, which is the radius of gyration. For a uniform thin rod, this is the information we have. And for different type of objects, actually you can find these already calculated values for the mass moment of inertia. The last thing that I want to talk about in this part is the composite bodies. Actually, we could have a rigid body that is composed of different bodies that are welded to each other, so rigidly connected. And in that case, what we can do is to sum these moments of inertia. One thing that you need to be careful here is that the sum should be made about a specific axis. So if you're going to sum up for this circular thing, then you need to use the same axis. You can use a different axis around here. So choose the axis and then sum the body's mass moment of inertia, and then you will end up with the total mass moment of inertia of that composite rigid body. Even you can remove the parts. In that case, you need to remove the mass moment of inertia, take the negative of that, and then sum it up. Actually, that's what that means. But still, the same information is true. You need to use the same axis for calculating all the mass moment of inertia. Only then you can do this summation or removing the parts.